Greeting teacher and everyone. So today we are going to do a presentation about the customer churn classification. So here is the table of content. So we are going to cover the objective, method, dataset, preprocessing, data visualization, modeling, model evaluation, model formula, and also final results. So next up, I'm going to talk about the objective. So churn refers to the number of customers who stop using a product or service over a given period of time. Also, customer churn prediction help to identify which customer are most likely to stop doing business with or using a company's products or service in the near future. So, a company can take like proactive measures to retain customer who are at risk of leaving. Also, churn predicts help uh, a company to focus more on the customer that are at high risk of leaving. So next up, I'm going to talk about the data set. So the data set that we use is called telecom.cvs. And it represents a collection of customer records from a telecom company. So each row of the corresponds to a unique. So each row corresponds to a unique customer, and the index column is the customer ID. The primary goal is to predict the target variable, which is whether a customer or has churned. That is whether they've left the company. This is a record as a binary label in the churn column with value yes and no. So the dataset includes a variety of features grouped into like four main categories. So first is the demographic attributes such as like genders, uh, senior citizens, partner, and also dependents. Next is the service information. There is a phone services, uh, internet service, and whether the customer use the streaming services. We also have the account information such as tenor, uh, monthly charges, and total charges. And lastly, we have the contract and billing details, like includes contracts, paperless billing, and also payment methods. So during the pre-processing, we found that the total charges columns had some blank strings, which we uh, converted to missing values and then filled with zero. So overall, the dataset is quite rich and provides a solid foundation for training machine learning models to predict churn.
Okay, so we talk about the method. So I have divided the method in eight clearly steps. So we load the data and initial inspection, and then we do the data cleaning as described, and then we have data preparation. So for this data set, we have four distinct type of data. So we have the ordinal data, the categorical, the numerical, and the binary. So we use data processing for each of them, and then we train and uh, we hyperparameter tuning of three gradient boosting models such as XGBoost, LightGBM, CatBoost using grid search and cross validation. And then we evaluate the model and we tune the gradient boosting models and on testing using classification metrics. And then we have a conversion of data to PyTorch tensors and creation of data loaders. So we start to do the deep learning model, and then we define and train a simple feed-forward neural network (MLP) for the model using PyTorch, and then we evaluate the model, and then that's it. Okay, next.
So moving on to the pre-processing steps before we so moving on to the pre-processing step before we know what to pre-process in the data. Initially we have to load the data first. So the data set that we use for this whole uh, model is the telecom.csv, and the code using Panda. Next. And while loading the data, we see some errors that we have to pre-process or fix. So the first one was the incorrect data type. As we can see in the picture here, the total charges is in object data type, but it's supposed to be in numeric. So firstly, we have to handle that data type by converting it to numeric and using coerce using coerce. And the second challenge was the missing value. These conversions reveal 11 missing values in total charges. So the solutions for this issue was to fill the missing value, which is in total charges column, with 0. And we use df.isNull dot sum. And moving on is the preprocessing pipeline. Column transformer. So the benefit of this step is to create a single preprocessing object that can be consistently applied to training and testing data. The concept is to apply different transformations to different columns efficiently. So there are 5 steps that we took. For the numerical data, we use the standard scaler to scale data to have zero mean and unit variance. And for binary data, we use one hot encoder. Uh, we drop first to avoid multi collinearity. And for the ordinal, we use ordinal encoder. And for nominal data, we use one hot encoder, which it creates a new binary columns for each category. And finally, for the remainder data, we use the pass-through, which is the senior citizen. So we keep that in the original form. And after the pre-processing step, we did the train, test, and split using the data that we pre-process. So the purpose is to evaluate model performance on unseen data, and the actions that we use in this step is to split the data into 80% training and 20% testing, and we use stratified k-fold for cross-validation, ensuring class proportions are maintained in fold, which is important due to churn imbalance. And finally, we further preprocess it using fit transform on training data, and then transform only on test data to prevent data leakage. And finally, after the preprocessing, we got the data in NumPy array for further model development. Because yes, so we successfully loaded the clean, explore, and preprocess data, and a robust preprocessing pipeline was also built. So let me walk you through the data validation step. If you take a look at these visualizations, we see that we visualize the target variable distributions, churn to understand the balance of the target variable. We see, according to this graph, we see that more people decided uh, not to stay longer in the apartment. So, and while there's only 26.54% that agree to stay longer. Next. And the visualize on numerical feature and distributions, we see that the tensor distribution is highly skewed, with a large number of customers having very short tenures, and another peaks at the maximum tenures, suggesting many customers either leave early or stay long term. The second graph, which is the monthly charges distribution, is more spread out but still shows a peak at lower value, indicating that many customer pays relatively low monthly fee, though some pay significantly more, just like you see the first line bar chart. And finally, the total charges distribution is right skew, with many customers have low total charges, which is aligned with the high number of short tenure customer. Next. Next one is the to visualize the key categorical feature distributions. So we can see that the contract distribution show that most customer on month-to-month plan, which may indicate higher churn potential compared to longer term contracts. In the payment method chart, electronic checks are most commonly used method. The most popular options, followed by DSL, with the smaller portions of customer not subscribing to internet service at all. Next, to evaluate and compare model performance, we also uh, plot the model's performance. The purpose is to compare the model, to understand the performance, and to select the best model. So the first method that we use to visualize is the XG Boost. So the Tune XG Boost model on 3 params, 3-fold CV, achieve an accuracy of 0.88 and an ROC AUC of 0.86, reflecting strong performance in distinguishing classes. The confusion metrics show 945 true negative and 194 true positive, but 179 false negative indicate a tendency to miss positive cases. This classification report reveal higher precisions and recall for the negative class compared to positive class. And the feature importance plot identify contract as the top predictor, followed by internet service, fiber optics, and online service number, while senior citizen has minimal impact, which is less than 0.05. And the next model that we used was the light GBM. So the two light GBM model achieve on accuracy of 0.80 and ROC AUC of 0.8584, indicating decent classification performance. And the confusion metrics show 937 true negative and 195 true positive, with the 178 false negative suggesting a conservative bias toward predicting negative. And the feature important plot highlights monthly charges as the top predictor, followed by total charges and tenor, while dependent, yes, has the least impact. Finally, the cat boost. So the Tune cat boost model achieved an accuracy of 0.89 and ROC AUC of 0.86, indicating strong classification performance. And the confusion metric shows 940 true negative and 201 true positive, with 172 false negative, suggesting a conservative bias toward predicting negative. And the feature importance plot identifies contract as top predictor, followed by tenor and monthly charges, while multiple lines, no phone service has the least impacts, which is less than 5. And finally, the LP training loss per epoch, we see that we see there was a significant decrease in binary cross entropy loss from 0.52 to around 0.37 over 100 epoch, indicating effective learning. The loss dropped sharply in the initial epoch and then gradually stabilized with minor fluctuations, suggesting convergence. So this trend reflects a well-trained model with improving predictive accuracy over time.
So next is the model that we use in our project, which is XGBoost, LightGMB, CatBoost, Free, and the last one is feed-forward neural network, which is MPL. So we try for different machine learning model to predict the churn. So this include the G, G, XGBoost, LightGMB, CatBoost, and feed-forward neural network, which is MPL. So each model has its own way to analyze the data. So we test all those to see which one is best performance. Also, next is how we evaluate the matrix. So we use many methods to evaluate which model is better to use, such as the accuracy to see how often the model is correct, and the second is about the ACU to see how well the model separate channel from non-channel. And the last one is about the S1 score. It balances the prediction to see the correct positive prediction and recall the finding churn. And as the result in the image below, and the model is uh, XGBoost have high accuracy, and ACU as one score is more than CatBoost, and then is the neural network.
Onto the final results of the models. So for XGBoost, the best parameters are n estimate equal to 100, max depth equal to 3, and learning rate equal to 0.05. The light GBM model best parameters are an estimate equal to 100, 31, a number of leaves equal to 31, and a learning rate equal to 0.05. For cat boost, the best parameters are iteration equal to 100, depth equal to 5, and learning rate equal to 0.05. All three models have CV or OC AUC ranging from 0 ranging from around 82% to 84%. As for the metrics, the accuracy for all models is around 80 to 81%. The precision for all three models is around 66% to 68%, and the recall for all three models is around 52 to 53%. F1 score ranging from 58% to 59%, and OOC AUC around 85 around 85 to 86%. For the final results of the MLP, the architecture is two-layer with 64 and 32 neurons with ReLU activation and a dropout of zero point 0.2 trained for 100 approach using a DOM optimizer and binary cross entropy loss. For the metrics, its test accuracy is 79.13% with a test loss of 43.33%. And the best model is the tuned cat boost because it has the highest ROC AUC and the highest F1 score on the test set, which means it's the most effective at balancing precision and recall while distinguishing between the trained and non-trained customers. And one more thing, the four models are difficult to predict because they are boosting in neural network algorithms. Next, onto the explanation of the math formula. First is the XGBoost math. It is a gradient boosting model. Its key math concept is the second order Taylor expansion of the loss function to define the optimization objective. And the objective function XGBoost minimizes at each step m when adding 3fm for a given data at point xi. It can be approximated using a Taylor expansion around a current prediction. This is the formula. The first part here is the loss based on the prediction from the previous m-1 tree. Second part is the product between the first order gradient and the prediction of the M tree for point I. The third part is of the the product of the second order gradient, the Hertzian, and the prediction of the M3 for point I divided by 2. And the last part is the regularization term for the M3, and then you sum all of this. Conceptually, XGBoost uses both the gradient GI, which is this, and the Hertzian HI to more accurately approximate the true loss function at each step. And this second order information, it helps determine the optimal tree structure and leaf weights more effectively, leading to better performance and regularization compared to methods used for first order gradient. The tree is then trained to minimize this approximate objective function. The next math is for the large GBM math. The core concept is also around minimizing loss function through gradient boosting. And this is the key formula, which is the target for the M tree. Why M here is the negative gradient, and here because it's negative because of the minus sign, and this refers to the derivative first derivative or the gradient of the loss function with respect to the prediction. So this is the loss function, and this is the prediction for the as data point after the m minus 1 tree have been added. And this negative gradient becomes the target that the M decision tree is trying to predict. Conceptually, each new tree is built to predict the direction of the steepest descent in the error space, helping model iteratively improve its prediction and minimize overall loss. Third is the CAT boost math, just like others, the gradient boosting model that relies on minimizing a loss function using gradients. Its key distinctive math concept is ordered boosting and how it computes targets to prevent prediction shift. And the core idea relates to how residual gradient for data point is calculated when training a new tree. The formula is similar to LAGBM formula, is a target for training tree M on data point I in order boosting, but the difference is here is the prediction for point I using model trained only on data points that appeared before point I in a random permutation using the first M1 tree. It's besides that, it's still the negative derivative of the loss function with respect to the current prediction for point I. And this formula calculates the negative gradient but uses a prediction built without seeing the target of the current point I or any points ordered after it in that specific permutation. And conceptually, this ordered calculation of the target YIM prevents the target leakage that can cause prediction shifts, especially with categorical features. And this makes the model robust and prevents overfitting. Lastly is the feed-forward neural network math. Its core formula is representing the operation within a single neuron in a feed-forward neural network. This is the equation, which is the equation of the output of a neuron. X is the input vector to the neuron. B is the bias term for that neuron. Weight is the W is the weight vector associated with the connections to this neuron from the input X. And this equation is the linear transformation, the weighted sum of the inputs plus the bias. And this symbol is the activation function. In other words, such as ReLU sigmoid tan, it introduces nonlinearity. And A here is the output activation of the neuron. And this formula describes how a single neuron processes input. It calculates a weighted sum, adds a bias, and then applies nonlinear activation function. In feed-forward neural networks, change this operation across multiple layers, transforming the data input through a series of linear and nonlinear steps to produce a final output. And this learning process involves adjusting the weights bias to minimize loss function using techniques like backpropagation, which relies on gradients derived from this forward path calculation. And that is all for my group presentation. Thank you. That's all.